So for today's presentation is actually the first one for this season, actually. And we are going to have a pathway in network science kind of talk. So the seminar of Human in Network Science, if you don't know, is an interdisciplinary seminar. We are looking forward to promote and showcase research by women and non-binary research in network science. And actually the seminar is open to everyone, and you can join the mailing list to receive announcement or the Zoom links. And this is organized by Alice, Echo, and Marie, and actually me. So if you, by any point of the year, actually, you think about someone who you would like to nominate as a speaker, or in the other way around, if you want to nominate yourself or you want to present something, please let us know, okay? We are looking forward to knowing more people. So for today's speaker, I'm going to say a couple of words, if you allow me. So today we have Raissa Souza, Associate Dean for Research from the College of Engineering in the University of California, Davis, USA. And she used the tools of statistical physics and applied mathematics to develop mathematics model capturing the interplay between the structure and function of networks, including dynamical processes unfolding on networks. Her work actually focusing the abrupt onset of large-scale connectivity in networks, network synchronization behavior, and model of cascading failure. The general principles derived provide insight into the behavior of real-world networks, such as infrastructure in networks and social networks, an opportunity to identify small interventions to control the self-organizing collective behavior displayed in these systems. She collaborates broadly with faculty within the college and in physics and statistics, but also political science and the Primate Center. So we are very looking forward for your presentation. I'm very glad to have you here. And yes, I'm going to give you all the time for you right now. And sorry everyone for the technicalities at the beginning. Hopefully this is not going to be happening in the next seminar. So go ahead. Yeah.
Great. Thank you so much for this invitation. It's great to see so many people here from all over the world gathered, some old familiar friends. So thank you for joining us today. So when Alice and Francesca asked me to give this talk, they asked me to talk about pathways. And I've spoken to some high school students before, and I revamped that talk. So my talk is, how did an Indian Chilean girl from Chicago become an engineering professor at UC Davis? So I'll tell you about my pathways. I'm also external faculty at the Santa Fe Institute and at the Complexity Sciences Hub in Vienna. And I'm going to try and speak for like half an hour so that we have plenty of time for an open discussion. So I'll just go ahead and start with my presentation. So my story is a classic story of being a kid of immigrants. And my story begins in Purdue University in the early 1960s. And this is my parents soon after they met at Purdue. And so my story is a story of three countries: India, Chile, and the United States. So let's start in India, where the first person in the story was born, which is my dad. And my dad was from Goa, which was a Portuguese colony until the mid-1950s. And it's a really beautiful fishing village type area with lots of palm trees and coconuts. And his mother really wanted him to stay there and be a fisherman. But his dad was an engineer who worked in Africa and Mozambique, as was pretty common back then. So my dad knew the value of education, and he was very gifted in math and science. So he pursued engineering, and he went to the University of Pune, which is right here. Hopefully you can see my pointer. And he got his undergraduate degree there in engineering. And then he was able to get a scholarship to come to the United States and get a master's degree at the University of Notre Dame. And he studied mechanical engineering, and he did really well. So he was able to apply to PhD programs, and he got into the PhD program at Purdue University and supported himself via TA and GSR work, and got his PhD in mechanical engineering at Purdue. And now we can go across the world to the very far north of Chile, to Antofagasta, which is also quite a fishing port on the opposite end of the world. And it's very close to the Atacama Desert, where we see these beautiful flamingos and high altitude lakes and geysers. It's really a very beautiful place, very connected to the earth. So my grandfather was a mining engineer, and my mother was very drawn by the earth and geology. So she went and also knew that education was her path out of Antofagasta. So she went to Santiago, to the University of Chile, and studied geology. And she was actually the first person to get a degree in geology from the University of Chile. So it was a new major back then. And she got a scholarship to come to the United States, and she went to Purdue for a year, which is that faithful place where she met my dad. And after Purdue, she got a second scholarship to go to Stanford for a year, and she got a master's degree in geology from Stanford. So you can see my academic pedigree is very strong. They didn't have a lot of money, but they had a lot of education to their names. So after that fateful meeting in Purdue and their long courtship, they married and they moved to Chicago, where my father was a professor of mechanical and aerospace engineering at Illinois Institute of Technology. And part of why I wanted to bring this up is that we grew up here on the south side of Chicago in an area called Beverly. So my Indian dad, my Chilean mom, my weird name, and we grew up in a part of Chicago, which Wikipedia attributes to largely English and Protestant, but it's a very thriving Irish American Catholic community. So lots of Bridgets and Jennifers and blonde, blue-eyed kids all around me growing up, and I was kind of the oddball with a weird name that nobody could pronounce. But we had so many Irish presidents, the O'Reillys, the O'Flahertys, that growing up, we would always get mail addressed to the O'Souza's instead of the D'Souza's all the time. So it was good experience for me to be different. And I'm going to come back upon that again, because you'll see that part of my ability to be a scientist is rooted in the fact that I've always been different. And it makes you willing to ask questions that other people don't ask. And it gives you a little bit of courage when you're the different person around everyone else around you, and you're there and you're speaking. So I'm going to come back to that again a little bit later on. So just to set the stage there. So when I went to high school, I knew that I needed to find a place that would meet my parents' intellectual rigor requirements, a college prep kind of place. But I wanted to find someplace a little bit more exciting and creative. So I looked all over the city when I was in 8th grade, and I managed to find a really amazing high school up in Lincoln Park, which is really very vibrant, multicultural, very dynamic part of the city. And I went to the International Baccalaureate program, which is a very rigorous college prep kind of curriculum at the Chicago Public Schools. So all of my life, I've gone to Chicago Public Schools, which was really great. And then after finishing high school, I applied to college like everybody, and I had really great grades and great extracurriculars. So I had my mindset on going to an Ivy League school or some fancy school like that, but I didn't get into any of them. So I kind of had to lick my wounds, and I went to my local school, the University of Illinois, which is obviously not a bad school in any way whatsoever. It's really a spectacular school, but I had my sights set higher. So I was the first kind of blow that I didn't get into any of these places. But, life goes on, and we enjoy the situations that we're in. And I had a wonderful time at U of I. And for those of you who come from the statistical mechanics side of network science, I'll tell you that I had the great pleasure that I got to take thermodynamics from Nigel Goldenfeld, who's just an incredibly inspiring person. And I think that really helped shape my future career trajectory, though you'll see it's a little circular. So it was a lovely class. It was the class I enjoyed the most, for sure. My dad, being a professor, knew about some opportunities. So he came home one day and he said, you have to enroll in this apply for the summer research program for women and minorities run out of AT&T Bell Labs. And that program started in 1974, and I believe it ended in 1994. And they've expanded things, and now they have bridge programs, but this particular program really led to a lot of women and people of color going into science. So I applied for this program, I got accepted, and I spent my summers doing research at Bell Labs, but in particular, we were working on lithography and chemistry. photoresists for lithography. So I spent a big bulk of my time at Brookhaven National Lab here at the synchrotron facility, where we were looking at the chemical properties of photoresists in order to print electronic circuits. And it was super fun. You know, it was the classic side of doing experiments, that when it's your time on the beam and your experiment is up and running, you are there 24/7. So, you know, we collected years worth of data to analyze in about 3 days of just the experiment running constantly. And it was really fun, fast-paced environment. And one of the really great things that I got out of the summer research program was, of course, first of all, an understanding that research is about asking questions that no one's ever asked before. So it's very different than learning in a classroom where you're doing problem sets and there's a solution key and the answer is known. So much more frontier, exploratory questions to pursue research. So that was the first thing. And then more practically, because I did a good job, we ended up getting a couple publications out of this work. And I also got really great letters of recommendation about my research skills. So with these things in hand, I applied to a bunch of grad schools. And I thought, if I don't get into a great physics PhD program, I think I'm going to become an environmental engineer because I really love being outside. So that was my plan B. But plan A worked out pretty well. So I ended up getting a scholarship to go to study a PhD in physics at MIT via the Hellman Fellowship. And here's a picture of looking from the big dome out at the Charles River in Boston. It was a really lovely place to be. And while I was at MIT, I started with this trajectory that guided me towards towards experimental atomic physics. So I had that experience at Brookhaven National Lab working on the beam. And so I started at MIT and I started working in experimental atomic physics with some of the leading faculty there. And it was fun, but I felt like it was very specific and I wasn't learning very general skills that would translate to new areas. So I was learning how to be like a really precise laser jock and crawling around on the floor all the time. And I thought, you know, I kind of want to think about bigger picture issues. And I started reading more broadly about science, and I came across a book that had a lot of impact on me. I think this book might not be so popular anymore because this was in the 1990s, and I came across this book, Complexity, Life at the Edge of Chaos. And it just opened my eyes, and it was all about complex systems and emergent behaviors. And it was written by author Roger Lewin, who writes popular science books. And he talked a lot about the Santa Fe Institute and their work on complex systems and emergence. And I was captivated. And I thought, someone at MIT or in Boston must be working in this field and affiliated with Santa Fe. So I started reading through all the proceedings of the Santa Fe Institute, looking for someone in the Boston area who could be a PhD advisor to me in the area of complex systems and emergence. And luckily, reading through these proceedings, I found the key. So the key for me to start moving into complex systems was working with Professor Norm Margolis, who was in the lab for computer science at MIT. And Norm was a real visionary. He was one of the first people to work on quantum computing. And with Norm, we worked a lot on cellular automata and looking at how self-organizing systems could compute. And I needed someone who was a little more down to earth and connected to physics. And I convinced Mehran Kardar, who's an amazing condensed matter theorist, that he would be willing to take me on as a student. So I did a small project looking at neural networks. And he was willing to take me on, which was really great because I had one advisor who was more freeform and incredibly untethered. And I had another advisor who was very pragmatic and very serious. So it was a great place to get mentorship from two very different personalities. And I learned a lot from both of them. And so my research for my PhD focused on thermodynamics and the emergence of structure and things like information processing and self-organizing self-assembly. So I was very fortunate. And I guess this is about pathways. So I just want to be very open and frank. And, when you start grad school at MIT in physics, you don't think you have the chops to be a theoretical physicist because there's a lot of hierarchy and elitism. And so the people who scored the very best on the entrance exams were like calculating machines, and they were the theoretical physicists. And more sort of, I wasn't the top student by any means, but I was probably one of the more creative students. And so it was a block in my mind that I thought, oh, I can't be a theoretical physicist because only those calculating guys are theoretical physicists. But it was really great that I was able to convince these two advisors that I could do it. And I had a very nice results that came out of it, exciting to me. So then it came time for me to search for a postdoc because I wanted to continue having the freedom to pursue research. So that was the next chapter, was trying to find postdocs and trying to decide which one to take. So I ended up having several offers for postdoc positions at various places. Probably one of the most appealing from a practical sense was that I was offered a director's fellowship at Lawrence Livermore National Lab, and it paid like $85,000 a year for a postdoc in 1999. That was pretty exciting, but I didn't want the salary to be the decision maker. I wanted these two things to be the decision makers. So I wanted to go someplace where I would have independence and autonomy to choose my own research problems. And I also wanted to be surrounded by excellent thinkers. So I wanted to go to the place where I would feel like the dumbest person in the room. And so of all the choices that I had before me, I ended up accepting a position at Bell Labs Lucent Technologies. And this was, again, in 1999, which was when Lucent was still very much a powerhouse, a scientific powerhouse, and still funding a lot of basic theoretical research that has led to several of the Nobel Prizes that came out of Bell Labs. So it was still very much in that ethos of discovery and freedom and inquiry. So I had a joint position that was between the fundamental math group and the theoretical physics group. So I had this position for 2 years. And when I was at Lucent, they build phone circuits and networks and ATM networks. And I started thinking a lot about networks and thermodynamics and self-organization. And so I did a lot of work on self-organization and ad hoc networks. And we patented an idea about how sensors could make sure that they were connected together and would span a region of interest. So that pushed me in the direction of thinking about networks, taking my skills from statistical physics and thermodynamics and thinking about self-assembly of ad hoc networks. And from Bell Labs, while I was there, I met a lot of very exciting people. And one of the people that I met was at Microsoft Research. And I really wanted to do a second postdoc with these great thinkers there. So I had an opportunity to go do a second 2-year postdoc at Microsoft Research in Redmond, Washington. And I was in the theory group there. And finally, for the first time in my life, I had a mentor, Jennifer Chase, who you can see is just an incredibly dynamic woman, and she's a real powerhouse. And it was the first time that I had any kind of mentor that looked anything like me, was a woman, first of all, and was just very outgoing and really very dynamic person, really high energy, and would take over a room, and very strong ideas, very rigorous thinker. So it was just wonderful to have her be a role model for me for those 2 years. And while we were there, this was now 2001. And while I was there had been a lot of really exciting work that just came out about networks. So preferential attachment, power laws in the World Wide Web. So there were things from the network theory side of things and things from the computer science side of the house that were launching this field of network science. So I had the opportunity to get in on the ground floor, I would say. So with Jennifer and Christian Borgs and a couple other postdocs, we started thinking about network growth dynamics. So we wanted to think about mathematical models of network growth, discrete time algorithms for network growth. And we thought about trade-offs, about why nodes would connect to certain nodes. So I think everyone knows the paradigm of preferential attachment, that the rich get richer. So in preferential attachment, a new node shows up and it attaches to the highest degree node it has access to in the network. And that seemed counterintuitive to how the physical world works. You don't want to connect to nodes that are overloaded. You want to connect to nodes that have some capacity to service and interact with you. So we started thinking about optimization ideas. So why would a node choose to connect to other nodes? And we looked at trade-offs between spatial distances and distance to the center of the network. And we ended up showing that we could give rise to preferential attachment from a more basic underlying optimization algorithm that traded off two metrics, the spatial metric and the tree metric. So that was the work that I did, the main work that I did with my postdoc. And we had the great fortune to produce a very nice graphic that PNAS liked. So they put us on the cover of the issue that month. And several people said, oh, they chose your work as being so important. And we said, no, they just chose it by the compelling graphic. So that's something to be said about keeping an eye open for how you're delivering your work as well, and the visual representation of your work. And certainly in networks, we've got a great advantage that we've got really amazing things to visualize. So that was the bulk of my postdoc, and it was so much fun. And working at Microsoft at that time was very free, and freedom to pursue whatever I wanted. And I was getting paid more or less like a Microsoft employee, which was also pretty nice. But postdocs always end. And that's one of the sad things about postdocs. They have, you don't have this weight of getting a PhD over your head anymore. You've accomplished it. You have freedom to pursue some new directions. And you've got all the knowledge that you've gained already. But the weight of over your head is the fact that you need to find an actual job after this postdoc ends. So that's the next chapter, was looking at the job search. So with my training, PhD in physics, postdocs in applied math, and theoretical computer science, I applied quite broadly. So I applied to jobs in physics, CS, applied math, and I applied to one engineering position at UC Davis because they were doing computational science and had several complex systems folks around. So it was a very interesting job search for me. So I would say that in physics, I did get a couple interviews, but not at very good places, not at very highly ranked places. Let me correct that. In CS, I got a couple of interviews at highly ranked places, but they kept telling me, well, if you're going to be a computer scientist, then you have to give up those physical review publications because those journals aren't going to be what gets you tenure. If you come here and you're a computer scientist, you have to be on the program committees of the leading conferences in your areas and focus exclusively on those. And the physics departments were giving me the opposite story. They were saying, oh, of course, Physical Review Letters is a great journal. Oh, fabulous. But what are these conferences and why are you publishing there? So I really didn't like that both of those fields were trying to push me to have to compromise and not pursue the work that I was most excited about. And in applied math, I don't think I got any offers, but I did get some interviews, so it wasn't an option. And I got this really intriguing offer from UC Davis to join the mechanical engineering department as a computational science and engineering person studying complex systems. And I thought, wow, that sounds pretty interesting. And they were very open-minded. They loved the physical review publications and they loved the conferences. So I was like, this is very interesting. And I come from this training of being a physicist from all of my degrees. And in physics, you ask some really great questions, profound questions. What's the nature of the universe? What's the origin of life? And I started acting with these engineers, and I found that they were also asking profound questions in a really different realm. So the engineers that I kept interacting with kept asking, how can I help people? And I thought, wow, that's incredibly refreshing to think about the next decades of your career having some foundation in helping others. And I thought, wow, this sounds pretty exciting. I think that I'll go ahead and take that UC Davis position. So I went to UC Davis, and I'm going to call that chapter 5. And I joined the mechanical and aerospace engineering department. And with my background in thermodynamics, I immediately latched on to teaching our undergrad and upper division thermodynamics classes, and also our mechanics classes with all the physics training that I've had. So those were very natural areas for me to gravitate to. And UC Davis is a very interdisciplinary place. So I started collaborating with people in computer science who were very engaging, and they said, we've been waiting for you to arrive. and they were studying online social networks of software developers. So we started a really fun project looking at open source software. And then I started interacting with political scientists who were really interested in network methods. And finally, in the last couple of years, I've started working with primatologists who study social networks of macaque monkeys. So it's a very interdisciplinary place, and I found tremendously great collaborators across different spaces. And even though I'm not a great fit in mechanical, they tolerate me and value what I contribute. And after I achieved tenure in mechanical, I wanted to align my teaching more with my research goals. So I asked if I could join the physics department, and I asked if I could join the computer science department. And physics was not terribly excited, but CS was, and they welcomed me. And I have a 50% appointment between mechanical engineering and computer science. And in computer science, I teach discrete math and probability and statistics. So you can see that my teaching now is really aligned with my research interests in networks, using approaches from thermodynamics and discrete math and probability and statistics to understand network dynamics, the interplay of structure and function. And I do have adjunct appointments in the grad group in applied math. So a lot of my PhD students have come from applied math. And I now actually am a member of the physics department as well. So it took 10 years, but they finally acknowledged that I am a strong member there, which means that I can advise students in all these areas. And I'm really excited because on the call, I see one of my previous students who worked with me and got a PhD in applied math, and that's Jordan Schneider. I don't know if he's still on the call, but he was here when we started. So really nice to see students moving forward. So as I said, it's a very interdisciplinary place. And here's a picture of my group from a couple of years ago when it was bigger than it is now. And there's Jordan. And so, like I said, my group can be very interdisciplinary. So I have students from physics, computer science, and applied math at the core of the group. And it's really great because the physicists really push the computer science. And we also do a lot of things. We do a lot of things with branching processes, and that's sort of shown here. And we like to think about the extent of connectivity in networks, the roles that different nodes play, vulnerability of networks to failures, and things like social dynamics unfolding on networks. So some of the main things that I work on are network connectivity, especially phase transitions in network structure and control interventions. So if we look at a network and we start from just disconnected nodes and we start adding edges between two randomly chosen nodes, we follow this trajectory shown by this black line here. What the y-axis is plotting is the size of the largest component divided by the total number of nodes in the system, fractional size of the largest component. And this is the number of edges that we've added to the graph. And as we add edges, we have a very lowly connected network, and we get to a critical point where there's a phase transition, and the maximum component transitions from being logarithmic in n, the network size, to being linear in n. And this is a classic result of Erdős and Rényi. And I'll come back and talk about this in just a second, in 2 or 3 slides. But with some collaborators, we were very interested in understanding how to manipulate the basic Erdős-Rényi random graph and delay the onset of connectivity. And we came up with some ideas and some algorithms and showed that we could successfully delay the onset of connectivity. But when it did happen, it was in a very unusual phase transition that happens in a very abrupt manner. So we called this explosive percolation, and it led to a lot of follow-on work and debate about whether this was a first order discontinuous transition or a second order transition. All the evidence before us at that point in 2009 suggested that it was a first order transition. So we put that hypothesis out there. Years later, it was shown that it's actually a second order transition, but with very unusual finite size scaling. And there's still more pieces to the puzzle that are being unfolded right now. And part of why this is so interesting to people is that connectivity of a network is such a fundamental aspect, and it can be a liability or an asset given the context. So if we think about, say, the internet or the world airline network, we want it to be fully connected. unless there's a virus propagating on that network, and then we want it to be disconnected. So at times we want to be fully connected, at times we want to be disconnected. A lot of what I do is also looking at cascading failures on complex networks. So looking at the paradigm of self-organized criticality to model things like cascading failures in electric grids or avalanches of neuronal firing in brain networks. I also do a lot of work on cascades of influence and product adoption and epidemic spreading in social networks. And in the last couple of years, in collaboration with my primatologist collaborators studying these macaque monkeys, we've been looking at, well, as cascades in social hierarchies. And the third thread of my work is really looking at emergent macroscopic properties that come from the interplay of the dynamics of the node in the network and the network connectivity structure. So the both of them combined give rise to emergent properties that we wouldn't see from the nodes themselves, from the network themselves, but it really needs the interplay of the network dynamics and the network structure to lead to these emergent behaviors. And what I'm showing you here is actually a nanoscale electronic MEMS device, and it's a vibrating membrane. So it has some amplitude and it acts like an oscillator. And we were looking at rings of these oscillators and found emergent behaviors. And part of this was from a grant that I had on predicting and controlling systems of interdependent networks that I'll tell you about in a minute. I thought I already had that slide, but I don't. So I'll tell you about that grant in just a minute. So what I did want to just tell you one lesson that I learned about this explosive percolation. And it wasn't that the transition's second order. What I learned about explosive percolation is that this was a really exciting problem to me. I was back and I started working on this in probably 2005. And I thought, this is really exciting to change the nature of a phase transition. And with my collaborators, Dimitris Ekliopoulos and Joel Spencer, we started thinking about the Erdős-Rényi random graph model, which I mentioned briefly earlier. You start with a bunch of disconnected nodes, you choose 2 nodes to connect by an edge at random, and you get this black phase transition with the emergence of large-scale connectivity. So we said, instead of choosing 1 node at random and adding to the graph, what if we choose 2 nodes and we select to add the edge that is more favorable and we discard the unfavorable edge. So at each time step in choosing 1 edge at random, we choose 2 edges at random and add the favorable one and discard the other. So if we want to enhance, here's 2 candidate edges. If we want to enhance, we would choose the edge that would result in the largest component. If we want to delay, we choose the edge that results in the smallest. And this delay leads to this explosive percolation. And actually, just in the last 2 months, I've done some calculations with some scientists in Bangladesh, and we can now show that this idea of 2 edges actually introduces a mechanism to maximize entropy. So it introduces a thermodynamic interpretation of network growth that's absent from the Erdős-Rényi. But the reason that I wanted to talk about this is I knew this was very exciting, interesting work, and nobody wanted to fund it. I wrote a career proposal about this. I got lukewarm comments from the physicists saying, oh, this is computer science, and the computer scientists saying, oh, this is physics. And they recommended that I go and work with the program managers and find some marriage between these different partnerships. And I thought, you know what, I'm just going to do it, because it's part of the beauty of doing theoretical and small scale numerical work was that I didn't need a lot of resources. So instead of pursuing grants to do this work, we just did the work. And why I want to say that is this is probably the most influential piece of work that I've done. And it was something that no one was interested in at the time. So there's going to be many situations in your life where you know you're working on something interesting, but other people don't understand it's interesting because they don't have that perspective and context that you do. Once we found out this result and it appeared in a high-profile journal, then suddenly everybody was interested in it. So just understand that you're the expert and you're the one who knows what the interesting problems are, and you've got to stick to that at times. So now people think this is an interesting problem. Lots of people have worked on it. And since then, so that was in 2009, that paper appeared. And then in 2013, I had this really great highlight of my career where I got to be the principal investigator on a multidisciplinary university research initiative that is put out by the Department of Defense each year. And they put out a call for controlling collective phenomena and complex networks. So you can imagine how excited I got about that. And it was a 5-year, $6.25 million project that I led. And our work was on predicting and controlling systems of interdependent networks, exploiting interdependence for control. So we really wanted to put the twist on there that no complex system lives in a bubble. All complex systems interact with other complex systems. And if we're going to understand any one of them or control any one of them, we need the bigger context. So we put together a really cool team of people working in statistical physics, control theory, information theory, civil infrastructure engineering, nanoscale device physics, and animal behavior. And we were able to secure this grant. And I got to lead this amazing team. So my fellow faculty members, co-PIs, were spread across Caltech, Rice, and University of Washington. And we had an amazing team of students and postdocs. So that 5-year period was really a super exciting time. And we got a lot of work done and built a lot of bridges across different disciplines. And so it changed me to start thinking more about control of complex networks. And we have a piece that's coming out, a perspective piece that's coming out next month in Nature Reviews Physics, which I wrote with Mario Di Bernardi and Yang-Yu Liu about control of complex networks with complex nodes. So trying to think not only about how the network structure influences the emergent properties, but how the nonlinear dynamics inside each node also does so. So the interplay of nodal dynamics and network structure fully taken into account. And last July, I started a new chapter in my life. So I'll call that chapter 6. So I'm still at UC Davis, but after some arm twisting and soul searching, I agreed to take on the position of being the Associate Dean of Research for the College of Engineering. So my official job description is that I oversee the research enterprise of the College of Engineering. And we have about 220 faculty members. We have thousands of graduate students and postdocs. And part of why I agreed to do this is that we had a dean who came in a year ago, and he felt that we needed a strategic vision that was not there before. So with my predecessor, who was the associate dean at the time, they did a big grassroots visioning exercise and came upon 4 critical problems that we face as a society that engineering is going to hold some keys to moving forward through. And those are enabling climate resilience, revolutionizing energy systems with renewables and integrating storage solutions, advancing human health, including digital health, machine learning, artificial intelligence, and transforming mobility, including the unmanned aerial vehicles that we're going to be seeing and air taxis and things like that. So I thought for myself, after coming out of this COVID era and working on things that I'm super excited about nodes connecting to other nodes, and what if these nodes have color and they have some preference of connecting to those of the same color, and how do these models connect at all to social networks or to critical infrastructure, I decided it was probably time to take a step back and focus on doing something beyond the small scale research that I could do, and think about how I can bring my complex systems, emergent behavior perspective to bear upon addressing some of these problems that we're facing as a society. And being, a person who studies phase transitions, I understand that we're at tipping points in so many different directions. So in July, I agreed to take on this job. So you can ask me next year whether I like it or not, because it's a big responsibility. It's higher level thinking as well. So this is the new chapter that I've launched upon in July, and I had signed up for 4 years, and I'm about 6 months in. So I just wanted to share some reflections with you. So way back when I started this talk, I was telling you how I've always been very different. So I'm a brown person with a weird name who grew up around a bunch of blonde, blue-eyed people. And then I went to University of Illinois and I studied physics, and there were 2 women in my cohort. So most of my classes, I was the only woman. Then I went to MIT, and same record. There were 50 students in my cohort, and there were 2 women in that cohort. So not a lot of women around. I've always been a weirdo. And I think that that's my superpower. So being different is an asset. Being original is fundamental to the creative endeavor of doing science. You can't ask revolutionary new questions if you're coming from the same background that everyone else has been in. You're going to have the same priorities and same context. So being different is really important for being original and moving science forward. And as I said, being different also gives you confidence because you're there and you're speaking and you're just present. And after a while, you just get used to being the only person of your kind around and don't even notice it anymore. So I feel like it's a superpower. And then I also want to say to be yourself. You'll be so much more happier and so much more productive if you follow things that you're excited about. I told you this story about it, following the path of studying explosive percolation, even though no funding agency thought I should be doing that, because it was really exciting to me and I wanted to do it. So if you do things that you want, you're going to be happier and more productive. And certainly one of the life lessons that I've learned is that nobody has a perfect life. Back in those Bell Labs days, there were a couple golden child researchers who were postdocs with me who were doing such phenomenal work. They immediately got permanent jobs at Bell Labs and big slush funds. And I was like, wow, I wish I could be one of those people. And then I got to be friends with one of them. And I realized that he suffered tremendous depression, clinical depression and insomnia, and was very disturbed. And I thought, oh my God, I got to just look at what I have and be happy with it. And I've learned this lesson over and over again, that anyone who you think has something that is a perfect life does not. So make sure that you follow the things that are good for you and don't worry what other people say or status symbols that they might think that you should value. And then I'd say the keys to my success are obviously passion and perseverance. But I think one of the keys to success right now in the modern world is having to manage distractions. So we're constantly having things beeping at us. We're constantly multitasking. Part of being a faculty member is multitasking. We teach, we do research, we do service, and they're very intertwined, and there's always fires. So a lot of multitasking happens. So learning how to manage distractions is really important. I always teach my large undergrad classes and tell people to practice distraction-free hour, where you turn off your cell phone. If you need to go to the internet, it's only for the task at hand, to focus on that. And I get a lot of comments from people, I don't remember thermodynamics, but I remember what you told me about distraction-free hour, and it's really changed my life. And it's something I like to practice as well. And I took a time management class, a very little quick one once, and I thought this was my takeaway from it, is that we've got things that are important and we've got things that are not important. We've got things that are urgent and we've got things that are not time sensitive. And we want to live here in this urgent, in this non-urgent, important quadrant where we can think our big thoughts, but everything pulls us to this unimportant urgent, especially in my new role as a dean. You can imagine I'm constantly getting fires to put out that are really not terribly important, but they're very urgent. So it's really important to protect your time so you can live in this quadrant down here, which is where the great thinking is going to be happening and the great research. And then I just wanted to make a comment about mentors. When I was a young person, I thought I was going to meet the magic mentor who was going to help me figure out the path of my life forward. But now as an older person, I realized that mentors come piecemeal. So there's not one magic mentor. There are mentors that you can turn to for all different kinds of reasons, especially now that we're living in this disruptive technology era that's very interdisciplinary, where we tend to change jobs more frequently than generations that preceded us. So there's no one who's forged the exact path that you want to forge. So you're not going to find a magic mentor. But what you can find is mentors for many different areas. So if there's someone who you admire for something particular aspect, I would encourage you to reach out to them. Maybe someone's a great public speaker, even if they're not in your field of research, but they're just such an amazing speaker, you'd like to get 5 minutes of information from them about what motivates them. Maybe someone's a great teacher, has great classroom style, and you can go and seek some help from them. Or maybe someone has leadership skills and, of course, scientific skills. So keep that in mind as well. And that's the end of what I wanted to talk about, because I wanted to save some time for some discussion and questions as well.
Thank you so much for that. I was super impressed for all the advice and all your experience. I was like, oh, okay, I like this sentence and this another one and this other one. So I really appreciate all your presentation. So people, I always invite everyone to share the reactions with the button in the Zoom link. You can applause or that kind of stuff, but also you can unmute yourself right now. I'm going to stop the recording.